Hey, well, welcome everyone back to the One World Minds seminar. Today we're very pleased to have John Harlim from Pennsylvania State University. John is a professor at Penn State in the Department of Mathematics, as well as the Department of Meteorology and Atmospheric Science. And he is also a member at Penn State of the Institute for Computational and Data Sciences. John has a lot of interests in applied mathematics, in parameter estimation, machine learning, manifold learning, operator estimation, data assimilation, uncertainty quantification, non-parametric modeling, and others. And today he's going to speak about diffusion maps on manifolds with boundaries for solving PDEs. So John, welcome to the One World Minds seminar. We're very pleased to have you and we're looking forward to your talk.
So thank you for the invitation and kind introduction. So for the attendees, thanks for being here. Saw a couple of names that I know. So today, I'm going to talk about this talk that I actually never talk about. This is just recent works that we are experimenting with diffusion maps, which is a method that was developed mainly for manifold learning to solve PDE on unknown manifolds. Okay, so let me perhaps, how do I do this? Okay, here. All right, so here's the plan of the talk. First, let me give you a brief overview of this diffusion maps as a manifold learning algorithm, in case some of the audience never seen this before. But at least Matt is super familiar with this because he used to work with Koifman, I believe. And then I'll talk about the recent work that we try, the so-called Ghost Point Diffusion Maps for solving elliptic PDEs. And these days, people also are quite, fancy of neural networks. So I'll discuss briefly what I do with this solver by finding the neural network solutions. And then I'll also discuss an application for Bayesian elliptic inversion problem on these PDEs. And if time permits, then I'll also tell you a bit about spectral Graph-Laplacian convergence on manifold with boundaries. Okay. So let's see. So first, so what is manifold learning? Basically, the idea is the following. So if you give a data and you assume the data lie on or close to a manifold embedded in n-dimensional space, that's the usual case, then the central task of this unsupervised learning algorithm is basically to characterize this data set. So in a way, you want to find sort of like it's dual or it's functional, how to describe this data. So here, as I say, if the data lie on the manifolds, then the manifold learning algorithm as one of this is basically to find a function or basis functions, apparently, to describe this data. So this is exactly what I say, it's just to find the dual of this space. So now diffusion maps, right? So what is diffusion maps here? This is a particular method, which is a nonlinear manifold learning. Basically, the idea is the following. If I give you data on the manifold, and then you have, let's say the data has a sampling distribution of Q. So here Q is a density function defined with respect to the volume form of the manifold. Then the diffusion maps basically is a kernel technique that give you sets of orthonormal basis functions with respect to this weighted inner product, okay, defined on the manifold. So the idea here is that these basis functions here are found by solving a eigenvalue problem as such. Okay, so here's the weighted Laplacian. Basically, we have like weighted by this density of the data. Okay, and if this manifold has a boundary, then usually this also satisfies a Neumann boundary condition in this case. Now, just to give you some other remarks is that if my data is the uniform sampling distribution, if the sampling distribution is uniform, i.e. the Q is constant or proportional to constant, then basically, this weighted Laplacian is just Laplace-Beltrami operator. Now, you might wonder, like, what's the role of diffusion maps in this case, right? Because it seems like, well, if you can just solve this equation if you happen to know the manifold. But this is where the diffusion maps comes. If you do not actually know the Riemannian metric or any parameterizations of the manifold, so if you're only given a sample data point cloud that lie on the manifold, then the diffusion maps comes handy. So it basically approximate this differential operator with an integral operator defined with some exponentially decaying kernel, like such as this, where epsilon here is just some bandwidth kernel parameters. Okay, so basically the key idea here of diffusion maps is as follows. So sorry, I just keep using this. So the key idea here is that there is this asymptotic expansion saying that away from the boundary, so if you're sufficiently far away from the boundary, if your function is at least C3 smooth on the manifold, then you can define this integral operator, okay? And this integral operator have the following asymptotic expansion. Basically, the first order is just some constant multiplied by the function itself, and then the order epsilon here, sitting inside of this order epsilon, you have this Laplace-Beltrami operator, and then the higher order epsilon square, where these guys are basically just depends on the induced geometry in this case. Okay, so then diffusion maps here, okay, is a discretization. So the way diffusion maps use this asymptotic expansion is as follows. If you define this L epsilon, this is just an integral operator here, right? Defined as follows. It's just this integral operator on the top here. You weight it by its normalization. You subtract by f, divide by some constant. Then Koifman and Lafont showed that this integral operator will pointwise converge in pointwise converge to the Laplace-Beltrami acting on the functions up to order epsilon. So one of the manifestation of this, the initial applications of this result was to actually use the eigenfunctions or eigenvector approximation of the discrete approximation of this as how to describe manifold, right? So now let me just give you an example, just a very silly example here to relate to what we know in numerical analysis, right? So suppose, if you have the data lie on uniformly distributed on a circle, right? Then you're trying to solve, in this case, what's the analytic, right? The analytic is like basically Q is uniform. So this is, you try to solve like Laplace-Beltrami, right? Eigenvalue problem on the circle, and we know the solution, right? So the solution for this is just sine, cosine, like e to the ikx, sine 2x, cosine 2x, and so on. So diffusion maps, use this data and construct this. So one of these dots, I guess, is the diffusion map solution, and the color here is just the analytic, just to give you sort of an idea like what this does, okay? So let's just say if the data is distributed Gaussian, so Q is Gaussian, then in fact, if you apply this with well-tuned enough, then you're approximating like Hermite polynomials, right, from the data. Okay. Then if your manifold is unknown, you can imagine that you're basically trying to get a generalized Fourier basis on a function that lie on the manifold, and they're orthonormal with respect to this weighted inner product by the sampling measure. Okay. So this is what it is. So now what I want to do with this is that first, I would like to use this property that you have this pointwise convergence estimation here to solve PDE on manifold. So, okay, so here's the first topic here. The problem I consider here is as follows. Suppose you have, elliptic well-post PDE. Just put all the assumption you like, so that is well-post. D-dimensional on compact submanifold of Rn. Basically, in the interior, you have this elliptic PDE. On the boundary, sometimes you might have Neumann, you might have a Dirichlet or Robin boundary conditions. Okay, so betas here are continuous real value functions defined on the boundary. Here, to be a little bit more general, L doesn't have to be just Laplace-Beltrami. It could be this weighted Laplacian. Okay, provided, of course, you have to know something about the kappa. Okay, and or maybe this advection diffusion type equation, which is this is precisely just the backward Kolmogorov operator. So here, this is just a covariant derivative in the ith and jth component, if you wish, and that's just defining the gradient. Okay, so one of this, basically, we're trying to solve this. Now, let's see what do we want to do here is the following, right? For this problem, there are many other approaches. Okay, so here's just some approach I'm listed just to give you some perspective. First, of course, finite element method, right? You can do this with finite element method. So here's a book, a long, very nice article by Zhu and Elliott here. So the idea, but here is the catch is that you have to know the mesh. So given the mesh, you do finite element method, it works beautiful, right? Now, these other three method, level set, closest points, or orthogonal gradient, I would categorize them pretty much as one methodology, where the idea is that you try to approximate the embedding functions that maps, your manifold into the ambient space. And then what you do is you try to write your PDE in terms of the PDE in the ambient space. So it might work, but the downside is that means it's like, if intrinsically you have 2D PDE, now you suddenly, at least you grow to the dimension, right? If the manifold has a codimension 1, no problem, maybe solving 2D and 3D maybe not a big issue, but it also depends on your solver, right? But if your ambient space is like codimension is high, then suddenly you have to solve maybe, high dimensional PDE on the ambient space, right? So here's the last method here, point integral method. This is, I would say, is probably the closest to what I will present to you. So this last method, this point integral, they are also sort of using this point cloud integral approximation, but I think they solve the method using variationals in the variational sense. The only thing about this method is like they have a way how to deal with Neumann and Dirichlet boundary, at least homogeneous. I saw that. But then for Robin boundary condition, I'm not sure how they deal with it. So there's never been, follow-up work on that. So that's all I can say about this. So now, right, let me tell you the basic idea and where's the pitfall first, right? So recall, like, this is the asymptotic expansion. So imagine, there's different type of asymptotic expansion, just slightly different derivation. So let's see. Let me say what I want to say here, right? Before, okay, in here, right, when I write this, I'm saying this asymptotic expansion give you Laplace-Beltrami. By a slightly different modification, you can actually get the weighted Laplacian. You can get these guys. You can get these guys. And also, there's a different variations where you can also get that L, okay? So for the next subsequence, I'll just use the same notation, this L epsilon here, as an integral operator to get one of those, either Laplacian, weighted Laplacian, or the non-symmetric Kolmogorov advection diffusion equations. Okay, so this is an integral operator that approximates the differential operator. Now, here's the very simple idea. We thought like, okay, we're going to do this pointwise. Let's solve the PDE. So here's the proposal. Like, here's your PDE, which is this guy here, right? And I want to approximate this in a differential operator with the integral operator, right? And if I am able to do that, then numerically, you will discretize this integral operator. So integral operator discretized, it become like matrix vector multiplications. So sweet, you can inverse this, right? Once you inverse this and see what happened, right? So that's what you want to do in the beginning, right? But there's a big issue here, okay? So I'll tell you what's the issue here. Main issue is the following. This diffusion maps asymptotic expansion that I told you before here, right? It only holds for manifold that are at least epsilon to the r away from the boundary. So epsilon is the bandwidth parameter. So here's just a simple example to demonstrate to you. So here, for instance, right, I'm trying to use diffusion maps to approximate these guys, this weighted diffusion operator on a semi-ellipse, okay? No boundary, okay, conditions on the, so this is what I'm plotting you here is just L acting on a function U without any boundary conditions, okay, on 400 points, distributed well sample, like equal space, equal angle actually, okay? So very nice, right? So you apply the diffusion map. So this is the red dot here on the left-hand side. What happened is that near the boundary, you can see there's a huge divergence here, right? So to be more precise here, like we look at the points, this is the boundary points, this is one end of the boundary. So getting to the interior, as you get to the interior is okay, but then closer to the boundary, this is basically, you know, diverge, right? Even the error in the uniform norm is about 13. So there's a huge divergence near the boundary. Now, in the following sequel of slides, I'm going to describe a new method, which we call Ghost Points Diffusion Maps, where you can see even at close to the boundary, you're there, and here's the error, like 10 to the minus 4, right? So this is one of the things that we want to be able to fix before we solve the PDE problem, okay? So how do we do this? Why do we call this Ghost Point Diffusion Map? So first, let me review you know, at least this is what I learned in numerical PDE, standard numerical PDE 101. So classically, right, this is a classical ghost point finite difference method. So I took this slide, you know, without permission from Long Chen. Basically, he has a course note he posted online. So I'll just look at it. So basically, this is what he plotted. Basically, suppose we want to solve this Poisson Neumann boundary problem, okay, boundary condition problems on this square. Okay, so this square is basically your domain. And usually, you know, you can define discrete approximation, find difference approximation to the Laplacian as, you know, let's say order h square if you want. But then, you know, you also want to discretize the boundary conditions so that they are higher order. So if you want to discretize only using first order, then you can use like one side difference, right? So the difference between this guy minus that divided by h. But if you want a higher order, you can actually approximate this guy by the following center difference, right? But when you do that, when you're, you know, write the tangential derivative as a center difference, what that means is that you introduce a fictitious point, right, or a ghost point here, right? 1, 2, 3, for instance. And the second is that means you're adding more points into your equation. So you have to specify at least the function value, right? We need to specify the function value at this point. This is the U0J that is in this notation. So the usual way, you know, one usual way that's specified in this course note is like, okay, you just write the PDE equation exactly at the boundary point, instead, in addition to whatever on the inside. So basically, you're trying to make this problem of the ill-post problem, right? You know, like you have like less equation than your unknown. So you're basically adding this extrapolation equation. So I call this just extrapolation because you need to figure out the function value out of the domain, right? So then looking at this, that means there are two steps here, right? There are two key steps here that is important if you want to employ a ghost points method. One is you specify your ghost points, okay? Two, you specify the function values at the ghost point, and then you can solve the PDE, right? Now, when the manifold is just flat, this is easy because you know the orientation, you know the normal vectors. Now, when the manifold is just embedded, let alone you don't know the manifold, you're only given like, sample data, then this is become a bit non-trivial, right? So at least you have to know how to specify this ghost point. So basically, recently, my former postdoc here, Xiao, he's now in Shanghai Tech, and so we have this method basically. So let me just briefly give you an overview what happened here. Basically, the idea is the following, right? Suppose this is your manifold, and this is your boundary of the manifold. Just imagine this cartoon, your manifold, you have a boundary. So what happened is like, when you're applying diffusion maps, when you're applying this integral operator, right? You're just integrating around local ball. So around in the interior, let's say this point is sufficiently away, epsilon to the r away from the boundary, this integral approximation to your differential operator is good, okay, in this region. But as you get closer and closer to the boundary, right, this integral becomes really bad because you don't have any more data to integrate here, right? So you're crossing, right? So our idea is like, okay, how to, extend this, right? Extend this manifold, okay? So that we can apply the ghost points idea in this, to correct this integral, basically, to correct. So I feel this is like a finite difference. It's like a finite difference, but in our case, it's just integral operator, right? So that's sort of the idea. So of course, first, we have to, so there are some technical tools here. Before you can do those specification of ghost point and, applying the extrapolation equations, you have to understand like how to estimate this normal direction at the boundary. So basically, first, the technical tool we need is given point cloud data on the manifold. And I mean, to be honest, I also assume I have data on the boundary, okay? If data are not on the boundary, there is a way how to do this, but I'm not sure how good it is, because we never quite tried, okay? It just, so here, at least in our numerics, we assume we do, and that's what we do, and in the algorithm we'll show you. And then you can approximate the normal direction out of the boundary. And then second question you have to understand is like, how about the well-posedness? What is this delta m, like, do they exist, right? Such a delta m, right? So I can, for example, right? So let's see, what time is it now? Just checking time here.
It's 2:55.
2:55, so I started 2:30. Maybe, maybe just a quick idea, right? Just to give you, so what do I mean by well-posedness? Suppose you have a manifold that look like this, right? Just imagine, right? And then let's say, we embed this manifold in R2 domain. Let's just say, the boundary here, this is my boundary on the bottom, and that's on the top. So suppose this is my embedding function, right? So of course, now let's say I was saying, okay, you want to be able to extend this manifold, right? Let's say, okay, we can extend this here, right? So here's your delta m. Apparently, in our formulation, it has to be, I mean, we specify it as the outer normal color of the manifold, right? Then, okay, when I extend this, right, these guys might extend to the interior, right? You can imagine that. Basically, how far can I extend this, right? So that this is sort of well-posed. Otherwise, it will create singularity. It's not embedding again. So basically, the technically is like, you want to make sure like this delta m exists. And then also so that, when you embed it in the manifold, it does not change the original embedding of the initial manifold, right? So there's technical things that you need to deal with, basically. But, besides this, I'm not going to discuss further more on this. You can just read the papers. Okay, so that's sort of what I meant here. And now let me continue. So once you have these technical tools, then you can actually specify the ghost point along, this delta M here, this fictitious extended outer color. And then also you can specify function values. Okay, so that's sort of our idea. Now, technically, so let me show you, how do you estimate the normal direction at the boundary, right? So if the data are well sampled, then it's fine. You can just use second line approximation. But if the data is randomly distributed, then we have a kernel method on how to do this. It's basically, the kernel method is basically, you take like a local SVD of like some sort of regression of kernel estimation. And asymptotically, you can show that basically the left singular values of those local matrix as your epsilon goes to 0, which is the kernel bandwidth, is going to converge to the tangent space. Okay, and then also the other eigen singular value, the next singular value, like the first D singular value will have the span of the tangent space, and then the next one you're going to have the orthogonal, which is normal to the tangent space. So we do that. So here's an example, right? So you give random data. So I'm just giving you a plot here on the left. This is on the semi-torus. So then this vectors here, there's a bunch of it are red or blue. I'm not sure which one is which, but maybe I think the red is the approximations and the blue is the true, right? So just to give you a little bit more detail is that, we can say, these things have an error of order epsilon half. We basically validate the theoretical convergence that we establish on this using the numerical approximation of this normal vectors, okay? So based on this, right, then the next is that you have to specify the ghost point. So how do you specify the ghost point? So assume, right, this cartoon here on the left here, like this is showing you, this is the manifold and here's the boundary point. So this is the this is the interior of the manifold. So that's the line, okay? Now, here is the delta M. Basically, it's like the exterior or outer normal color of the manifold, right? So here in this normal color, ideally, you want to specify your ghost point. So we also specify ghost point like, outside here based on this, very simple linear extrapolate, linear specification of the manifold. And we also put one interior ghost point because we need it for the extrapolation condition for the convergence. So basically, in order to do this, you have to also sort of like choose a parameter h, where we use some sort of KNN method to do that. This is ideal, okay, on the left-hand side. This schematic is ideal on near each of the boundary. This is what you want to do. But in reality, we don't get to do this because we don't know what is the true normal vectors, right? You don't know. What you have is just approximation, right? So when you have approximation, then you have no other way by specifying the ghost point on the approximate normal vectors. So then, you have this approximation to that, and all of this error, need to be accounted one by one in the analysis, right? So to do that, then we need to specify, for instance, if you have a function that defines smoothly on this sets, then basically you have to define sort of like an extension of the function here. It's like the function on the point, original point, and at the boundary, you're okay, like the function itself. And then, but at the ghost point, this is the quantity you need to approximate, right? You need to approximate the function value at this approximated ghost point. So there's a couple layer of error estimation here, okay? So, just to give you a little feeling, right? So what's the extrapolation equations? Remember, in the flat domain, the extrapolation equation I show you, one from the textbook, was just the finite difference discretizations of the Poisson equation at the ghost point. So we add that here, like this is our sort of, diffusion maps discretizations of the Poisson equation, if you like, right? That's the elliptic equations. But since the number of ghost points is not just one, there could be many, then we need more. When you search in the literature, then usually, you know, how people do it is like they're matching. Here is like a discretization matching second order derivative. So we do that. So we just do this, right? So now that you can see why we need this interior ghost point, right? Because we need to match this second order derivative here, right? So you need to match the order derivative in here. So you need to match that basically, okay? So this is why we need this interior ghost point. Then you can deduce error estimate of here's just the extrapolation error. Okay, so when I write order 1, 2, 3, 4, 5, this basically just mean order h cubic plus order this plus order that and so on. The last three order, the black one, this is standard from the diffusion maps asymptotic expansion plus the discrete estimation of Laplace operator. Now, this blue one, this error estimate is basically the dominant error if your data point is actually well sampled, meaning they're equal angle, very nice. Then you have a much better error rate in terms of h, in terms of the length of your ghost point discretizations. This, guys, is the error rate for random data. So if you really just given random data, you should basically just care about this one. So this is what we can deduce in high probability as epsilon goes to 0 after the data goes to infinity and the size of h goes to 0. Having this, then you can deduce consistency and so on and so forth, right? So, but here's our ghost point diffusion maps estimator. So suppose that U, okay, is a vector, long vector that consists of the function value on the manifolds and function value on the ghost points. So very long vector, right? Then the point of the extrapolation equation here, remember the point of this is to specify the function value of the ghost point, right? So in compact form, these guys, let me write it this way. The function value at the ghost point is equal to this, you know, affine equations. A function on the manifold plus some b, okay? Now, if you apply this discretization, so this is just a Graph-Laplacian discretization using the diffusion maps on, you know, all of this data, including the ghost points, then you can construct this non-square matrix here, and you can write this L as follows, where L1 is just the component that acts on the function value on the interior, and this acts on the function value of the ghost point. Then if you plug in this equation here, you get this affine equations, okay? So looking at this, then basically we define our ghost point diffusion map estimator as this affine operator, okay, as follows. So basically LG acting on n-dimensional functions or factors, sorry. So this factor consists of function value on the interior, okay, can be written as this affine, you know, map, right? So it's not a linear map approximation anymore. This is like affine map, and they're non-symmetric and so on, right? So now if you do this, you apply this, right, to solve this elliptic problem that I discussed before, right? Then basically we apply this elliptic problem, you discretize this, you know, using some kernel method, then we can prove. There are a lot of things, basically. There are many theorems. I just give you the simple one here. Basically, F and G has to have different kind of Holder regularity in this case. So for the case of Dirichlet problem, you know, when A is 0, for instance, you know, L satisfy maximum principle, or for Robin condition, this beta has to be positive. For Neumann, this is the case, you know, then basically you can show the convergence of this approximation in high probability, okay? So that's sort of, you know, thing that you can do about this. And then here I'm just giving you an example. So here's an example. I apply this advection diffusion equation, so it's non-symmetric, on the semi-torus randomly distributed data. So it's just 128 square. There are two boundary conditions. One of this is Dirichlet, the other is Robin. So mixed boundary condition here. So what I show you here, this is, I guess this is just the error. This is just the error. You can see the scaling of the error here. If I use just basic diffusion maps, being modified already. if you don't modify the diffusion map, it doesn't work at all because they don't respect this boundary condition. So we have a way how to modify it. We put it in appendix on paper, but it's not that important. It's already improved somewhat. And this is our method. Like, then you can see the error is going better. So it's the convergence rate as a function of n and so on. So there are many more examples in the paper to validate this technique, okay? Now, for the time being, let me just move on a little bit. And these days, people are neural network seems to be fashionable, so we'll try to do that as well here. So let's see, what's the setup here in terms of notation is as follows. Suppose you're given this point cloud data, okay? So I define this function phi, okay? This is my neural network model to be basically a factor value function on this parameter theta, okay? This is evaluated at each points where, what is this? This is just compositions of, neural network compositions of a bunch of activation functions such as ReLU. So basically in this very compact notation, theta is just corresponding to the parameters, okay, to the parameters in the neural networks, basically, okay. So for instance, you use ReLU as this thing. So what do we do with the neural network, right? What do we do is just the following. Let's find a regression solution to this PDE problem. So for simplicity, let me just describe this on closed manifold, so you don't have to worry about the boundary, okay? So the idea here is that, basically, you want to solve this equation in the regression sense. And in order to do that, empirically, you have to discretize all of this, right? So then basically, I use the diffusion maps to discretize this differential operator. So it acts like a finite difference, of course, through an integral operator. So that's the idea. So we approximate the PDE by solving this empirical loss functions, okay? So let's say, here I define theta s to be the global minimum of these empirical loss functions. I didn't say that I can get that, but let me define that, right? So then basically, we use the theta, the phi at theta s as the solution, okay, at theta s. Now, in the first trial, I'm a bit skeptic about this. I don't know how useful this is, right? But then, I collaborate with this, my Haichao Yang here. Apparently, his student is doing all this numerical simulations in detail. So basically, we just try this a little bit on the torus, 2D torus, a equal to 0, the kappa is such, this is the kappa. We just try this a little bit. We just want to know. I just want to know, like, what's the advantage of doing this, right? This is suddenly you're solving a non-convex, very high dimensional nonlinear optimization problem. So here's what I can see is the following. If you use the diffusion maps, right, I already show you sort of the forward error. So this is sort of forward error of the approximation of L. But now here's what we call the inverse error, is basically the solutions now, okay? When you use diffusion maps, you have to invert this matrix, isn't it, right? So if the matrix size is bigger and bigger, right, here is 20,000, right, with this discretization, you have to inverse this 20,000. Of course, it's sparse matrix, but that's slow, like beyond that is quite slow, right? Then basically what I can tell you is like this neural networks is give me a way how to get around that inversion problem by solving a regression problem. So what we found is like, here you go, if you use diffusion maps until more than this point, I may have computer capacity, but I have to wait for a couple of days, basically. Okay, so here's sort of like a time, but at least with the neural networks, now you can do this quickly. How quick it is somewhere here. But then also here you can actually test your error not on the training data, also on the new data. Okay, so because your solution now it's not just factors, right? In the previous method on the GPDM and so on, you're inversing a method, inversing a linear equation like finite difference. So what you get is just vectors, but here, what you get is actually functions. So you can test them on different points if you happen to have more points on your manifold. So basically what I can tell you is those are the two advantages that I've seen on this. Basically, one is that when you increase the data, you can do this by solving inverse problem faster, basically. So it is detail on this. Let me not dwell in it. Then we say, okay, fine, let's write some theory. So theoretically, what I can say is the following: if your solution of the PDE and kappa is all like smooth enough, C4, and of course L2, and your this is Q is your distribution of the data is at least continuous, then we can say with probability higher than 1/n minus 2, n is the size of the training data, there exists a ReLU network of the following width or depth, okay, one of this, so that at least you can say the U evaluate on the training data. So this is not generalization. This is just on the training data is consistent. Okay, so this is your ReLU network on the training data is consistent with your training data. This is a rate, whatever this rate. Okay, now basically here, because yes, I say there exists a sufficiently large network. Of course, there's a big assumption here. If this parameter global minimizer of this, right, is attainable. So I didn't tell you whether it's attainable or not, right? Then this training is consistent. Basically, that's what this theorem is about, right? In uniformly sampled data, then what we can learn is like, basically, we need neural network of the following width. Here's the number of parameters in neural networks. So basically just saying like, you can, do a good training for sufficiently wide or deep network. Now to achieve the same accuracy, then, balancing this error bound, that you can see, that you can find that you need how many training data, which is this, okay? Now we also have another propositions that I'm not showing here, is like, that give you a global convergence of gradient descent for a sufficiently wide two-layer neural network, so that this theta s is attainable. Okay, but what we proved there is gradient descent method, and it seems there's still a gap, right? Because when we do numerics, we are using SGD. We're not using deterministic gradient descent. So that's all I can tell you about this, right? So how am I doing with time here?
It's 3:15, so you'd have maybe 10-15 more minutes.
Okay, 10-15 more minutes. All right, so let me talk about this, guys. This is also, then we say, okay, why do you want to solve the PDE? One of the application is we want to do Bayesian elliptic inverse problem. All right, so the idea is like, here's for example, this is just a canonical example. You want to solve, you're given this PDE, you want to estimate this guy, theta, diffusion coefficients. Given also that noisy observation. So Y is a noisy observations of U, okay? Where D is just denotes an observations map in this case, okay? Now the inverse problem here is basically, you want to estimate the posterior distributions of this guy, this theta here, okay? Through some Bayesian formulation. So here is it. So I'm just writing here the posterior distribution, write it in the sense of Radon-Nikodym with respect to the prior distribution is given by this likelihood function. So this likelihood function is telling you how good you are, how good is your parameter to the data. What's the fitness of your parameters to the data? So Y is the data. So what is this F? F is a forward map that takes your parameter theta that you want to estimate into your PDE solutions, and D map, the PDE solution is the observation map to Y space. Okay. So I should say that the theta here is actually, in our case, is a function. So it's not just a finite number parameter. So what we're trying to get is basically an infinite dimensional object here, okay? Then basically there are two things that need to be done. One is, how do you specify the prior? So in this case, I collaborate with Sans Alonso and his student Rui Yang. So they say, okay, do this type of Matern prior. So this Matern prior is just Gaussian zero with certain covariance that respect the geometry of the data by some inversion of this Laplace, okay? Then the other thing is that you need to specify the forward map, right? You want to solve, given a parameter, you want to solve the, you want to evaluate this, because what we do here essentially is you're trying to do MCMC. So if you try to draw a sample out of this distribution, pi y, out of posterior distribution, then what you need to do is the following, right? Draw a sample of theta from this prior, and then you plug that theta into your PDE and solve your PDE. So you need a forward solver, and then evaluate this likelihood function and see, are you good enough or not? If you're good enough, we accept you. If you're not, then we throw you away. Basically, that's the standard MCMC. So we do this. So what we did is basically we applied the diffusion maps to solve this forward map. And we also have a different type of prior specification here for that. So I'll tell you a bit more. Just to give you an example, a quick example. So this is earlier work on manifold, on closed manifold. So this is unknown manifold. So we try to estimate the kappa, which is defined as exponential to the theta. So this is the kappa. The posterior mean is this. The truth is that. Okay, so here's the truth. And this is our estimation using this MCMC method, employing the diffusion maps as the PDE solver for the forward map. And you can see the error, so scaling of the error, it's a bit small, standard deviation, and so on. And recently, we basically extend this on manifold with boundaries, okay? So to solve a problem with Dirichlet boundary condition, for example, right? First, obviously, my forward map, which is the PDE solver, I have to replace. So I replace it with this Ghost Point Diffusion Maps. And then how about the prior specification, right? The Matern prior specification earlier I gave you is basically, I say theta, draw it from a random distribution of Gaussian with certain covariance, right? So we basically use like a Carhonen law expansion of this. So if you don't have a boundary, you just ignore the second term. Okay, you can just ignore this. But now if we have a boundary, right, then the Carhonen law expansion, you have to write it down as linear superposition of eigenfunction that respect the boundary. Okay, so this is the Dirichlet-Laplacian. So you need to solve this given only point cloud data. Of course, you don't know the geometry. And also you need this expression, right, for the boundary. So for the boundary here, what we do is basically we solve this harmonic equations. It's like standard PDE 101, right? You just solve the harmonic equations where you penalize one side of the boundary. So here, imagine I have two boundaries, separated, well separated boundary, beta 1 and beta 2. Just imagine semi-torus, right? So because that's what we do in the numerics. Then you basically solve all of this harmonic equation subject to functions, some functions on the boundary. What is that function? Is basically solutions of this approximation of this diffusion maps on the boundary. So here the boundary is compact, so no problem, a closed manifold, so no problem, right? So how we do this? Basically, here we use GPDM to do this. This we use the diffusion map. So the order of work is actually from backward. So you first have to solve this guy first using the diffusion maps. You get the eigenfunctions, and then you use the GPDM to solve these harmonic equations. And this guy, independently, there's a truncated diffusion maps. I think I'm running out of time to talk about that maybe. But so you have the three basis function to represent a parameter in here. Okay, so that's how we do this in a very in the setup basically. So here it's just an example, right? So let's say noise is about 0.01, 10%. N is 1,000, so 1,000 data. So this is semi-torus. Okay, so what I'm showing you here on the top, this is the true parameters. Okay, on the PDE, on the semi-torus, look like this. If I use the forward map to map the true parameter to the true solution, it looks like this. Okay, so there are two boundary conditions, I think, on the far end. So boundary condition here and on the back end here. So there are two closer. Two boundary condition. The other side is just periodic because this is semi-torus. Okay. So now what I'm showing you, you do this MC using this method specification of prior. Here's the posterior mean. Like, look, you think this is actually looking quite bad, but if you see, so I'm showing you a couple of plots. 97.5 percentile of our sample look like this. 2.5 percentile look like this. But this problem is quite ill-posed actually, because if you fed these three parameters into your forward map, they all look very close to the truth. So you can see this is pretty much is quite, ill-posed. So this is one example. There are many other examples in the paper. But am I running out of time? Or
I'd say a few more minutes. It's 3:23.
Okay, so let me try in 5 minutes. Okay.
Okay.
Sorry, keep you.
No, that's fine.
Okay, so last is actually spectral convergence of. So you can see here, right? Basically, I need to solve this eigenvalue problem subject to Dirichlet boundary conditions. So one way to do this is via a truncated diffusion map. So you just truncate diffusion map. So what do I mean by that, right? So here, I'm going to define, let's say I've given a Gaussian kernel here. So I'm going to define a symmetric kernel. So we symmetrize the kernel this way. So this is the definition where D is just a normalization, right? It's just the integral normalize it. So this is symmetric kernel, called K hat. And numerically, right, of course, this is just an ideal situation because, you cannot compute this D analytically. So numerically, this is what it is, right? This is the discretization, okay? So we're going to use this kernel, K tilde epsilon. What I can tell you is the following, okay? So I'm going to define a symmetrized Graph-Laplacian like this, exactly like this, U minus this, okay? Now, we call this L tilde epsilon n. So this is just a matrix multiplied by a vectors, if you wish, okay? A function in this case, I write it in that way. Now, if you also reorder the data, so that this is just the data on the interior. So you have n data, but let me just take subsets of that data, okay? Interior. Then basically, I define a truncated, this symmetrized Graph-Laplacian matrix. This is n1 times n1. So you just truncate this matrix, okay? You don't redo diffusion maps only using this data, no. But you do diffusion maps using all of the data so that the weight, all of the data, the weight are felt actually in here. So this is, you weight it, on the whole data, but then, you truncate this matrix. So if you do this truncation, right, then we call this matrix L epsilon n with O, just interior, okay? So there is smaller size than n. What we can show is the following. Let lambda be the eigenvalue of the Laplace-Beltrami, lambda I tilde, eigenvalue of that guy, okay, the tilde, which is this, eigenvalue of that, and let L epsilon O be oh, I missed an O here, okay, typo, with an O is the eigenvalue of that guy, okay? Then we can show the following. For closed manifold and manifold with homogeneous boundary condition and uniformly sampled, so this is just a uniformly sampled case, you have an error rate like this, spectrum error rate like this. And then for homogeneous Dirichlet boundary, this is your error rate the same, but the number of data is n1 because now we truncate the data, right? Now the proof of this, we use a standard min-max argument, which allow us to do so because our configuration of matrix L is identity minus a compact operator and symmetric, okay? The other piece that we use is we use also spectral convergence theory of integral operator from Rosasco and Belkin. So we have this couple of also weak consistency for manifold with boundary. This is a result by Vaughan, Berry, and Antil. So basically, there's a way how to get this spectral convergence to be in order. Now, a couple of remarks is that for closed manifold, the rate can be improved actually to the order of this. Now, basically, this is competitive with what they have here on this paper. And if we follow the method used in this paper, we can also deduce convergence to eigenvectors. So we have the rate. Again, this rate can be improved for closed manifold, but for the other, manifold with boundary, that's sort of the rate. We also extend it to non-uniform data. So non-uniform data is a little worse. The reason is because you get worse by this extra factor of 1 minus n to the minus 1 over 2d, because you need to estimate the sampling density on top of, the Laplace-Beltrami, okay? Because you need to debias them, okay? So I think I am close to the last slide here. So here's an example. We've done this on homogeneous Dirichlet-Laplacian. So the Neumann case, I don't want to show you because it's everywhere on the literature, but this is the Dirichlet. So on the left, I'm showing you RMS error of eigenvalue as a function of n. I believe this is the first 10 eigenvalues and so on. And this is eigenvectors. I don't quite remember. I think in L2, the eigenvectors in L2. Okay. So here's what we found numerically by truncated this, and this is randomly sampled data. We have this. So because this is random, then you do the experiment many times. So when you have really small data, there's a large more variation, but in the end, you still have this slow convergence. By the way, the theoretical prediction is this. So if you have 2-dimension, this is 2-dimension problem, then this is n to the minus the 10th. So this is still a little bit faster than that. And here's just a spectrum. You can see the spectrum here for this semi-torus example. So the true spectrum is the blue. If you use well-sampled, the nice data on Earth, then you get quite a nice convergence. If you use random data, sure, there's some error, deviation, right? But maybe you want to see the eigenvectors. The eigenvectors is so on. So here, what I show you is a semi-torus example. On the top and bottom, that's the Dirichlet boundary conditions. So this is, we estimated from the truncated spectral Graph-Laplacian. This is eigenmode number 10. On the bottom is eigenmode number 20. The analytic is on the right-hand side, okay? So we compute this semi-analytically. And if I want to compute error, then I have to interpolate this guy that come from truncated spectral Graph-Laplacian into the same grid as the analytic, right? So this is a Nystrom interpolation, and so that you can compare the middle and the right-hand side. And that's how we actually compute this error in the eigenvectors, because otherwise, right, they're on different points, right? So that's all it is. So let me close the paper by just telling you, here's a reference. Mostly the first part of the talk, I was just talking about this. It will appear in CPAM. And I didn't talk about earlier work here on the closed manifold. And then I also have this student, Chile Yan and Xixiao, we are also extend this on scalar value function on time-dependent advection diffusion equations. The neural network stuff is basically a joint work with Songwei Liang and Haixiao Yang. And then this Bayesian elliptic inverse problem is these two papers, SIAM, and it will appear in inverse problem here. And the last part of the work, the spectral convergence with my latest student here, John Wilson Peoples. So that's it.